Cool. I'm the last talk of the day. I know we're running a little late, so I'm going to try to be quick. I'm actually going to start a timer on my phone to make sure I'm good on time. But we do have a lot of content, so we are going to go quick. My name is Evan McBroom. I work for Spectre Ops. I'm a systems developer. What that means in my daily job is I write a lot of Windows code, a lot of C++ code for red team operators to use. I work on a team called the Internal and Community Products team. What that means is I write red team tools, again, that we use both internally, but we try to open source as much as this tooling as possible. Some of these tools you may be familiar with if you do work on a red team, such as the Mythic C2 platform, or if you write a lot of reports for clients, the Ghostwriter report management software, some people use that. Usually in my talks, there's a lot of people and a lot of open source research that I like to thank up front, but for this one, there's only one person that I want to do a big shout out to. Of course, Benjamin Delpy, the author of Mimikatz, has empowered a lot of mitigations in Windows over the years, and he's informed a lot of this research today. So big shout out to Benjamin. Now, there's a lot of presentations and content already out there on LSA and recovering credentials from that. So why should you care about this one? Well, with all the open content that we have, there's still a large gap. You're going to have content for things like logically getting creds from LSAS, and we're going to cover some of that today. You're going to get stuff like, well, there's stuff out there for like offline cred recovery. So when your laptop is turned off, how to go from the hard drive to creds and other stuff. But the gap that we have is, what if you have an online laptop, you have a user logon session, let's say you got some memory for LSAS, where do you go from there? Much of the open content out there is read the Mimikatz source code. And there are issues with that. When Benjamin wrote Mimikatz, he did it as a personal project. It's clear that there's no intention in that project to have readable code, and that's okay. It's a personal project. No one should expect that from him. But at the end of the day, it's hard to follow. Another issue with Mimikatz source code is he reverse engineered a lot of structures. That's expected and okay. But we're going to talk about in a moment some resources that we can use to get the actual structures that Microsoft internally uses. And if you take that and match it up to Mimikatz source code, because it was reversed in that source code, they don't match up. And so it becomes a very difficult resource to use. So one of my goals for today is to give you roadmaps of how the data structures align in memory for LSAS using the actual Microsoft data types, such that if you are tasked to write your own equivalent to Mimikatz without using that tool, how would you go from a memory dump to creds? Now here's where we're going to get today. We're going to have a very brief talk about how user logon sessions occur on Windows. We're going to only cover enough to do the rest of the presentation. Then we're going to talk about all of these different data structures. That's going to be the meat of the talk. It's worth, after this, talking about different mitigations that Microsoft has implemented to try to prevent this activity. And then once we present that, we'll show you some bypasses that you can use to get around those mitigations. Now, I mentioned that there are sources that we can use to get the actual data types that Microsoft internally uses for LSAS as well as the rest of Windows. I've learned that for some people, these are used on a daily basis, but for the larger industry, it's somewhat unknown. So it's worth talking about where I'm getting this information. The first thing is there have been leaks of Windows source code. You can just get them from GitHub. We have leaks from NT 3.5 up to 5.2. There's a few missing versions in there. I believe we're missing 5.1, but for the most part, old versions of Windows, you can get the source code for. It's hosted by Microsoft on GitHub. One popular thing you can search for is the Windows Research Kernel to get the version 5.2. That is a great resource because these structures have largely remained stable up until Windows 11. There's been a few changes we'll talk about, but for the most part, the design is the same. Another thing that came out in the last few years is at some point, private PDBs were distributed outside of Microsoft and uploaded to Web Archive. I don't know why that happened, to be honest, but these exist on Web Archive, so we're going to use them. And even though they're older versions of Windows 10, they match up a lot of the times with Windows 11 24H2, which is fantastic. Microsoft engineers also put out a lot of patents. You can find a lot of patents on the LSA logon processes, and that's not going to come up a lot in this specific presentation, but it has informed the understanding of how these logon processes work. They're very helpful. So if you want to get the engineer's perspective from Microsoft, these patents are super helpful. And lastly, we can never get away from reverse engineering. On the slide, you see that we have private PDBs from Windows 10. That's fantastic, but we're dealing with Windows 11, so we have to go to the 24H2 modules, open it up in Ghidra or your tool of choice, and just see, does everything appear to be the same? We have some secondary resources. Mimikatz is a great starting point. We also have something that I maintain called the LSA Whisperer Development Kit. If you go to that repo, you're not going to see it at first. Go to your branches. Right now, change that branch to version 3, and you're going to see a directory called LWDK, the LSA Whisperer Development Kit. What that is taking the private PDBs that you see on the screen, dumping out all the data types that relate to credential recovery that I could find or think of at least, and organizing it into a library that you can use in your own code. So almost everything you're going to see in this presentation, if you want the full types, go to that development kit. Lastly, of course, there's amazing content already in the open source media. So conference presentations, great. We're gonna have references to a few of them here. That's it. Let's dive in. So on Windows, to have a user logon occur, we have one large component, LSA, which people usually refer to as LSAS, the LSA subsystem. You're also going to have an application that's going to have some knowledge of user creds. This is usually WinLogon, and it's going to send these creds to LSAS to actually authenticate the user. That's going to be picked up by this undocumented subcomponent called the Security Package Manager. You're not going to find any documentation on it, but if you look at the old source code leaks, you can read how it works. Essentially, the SPM, the Security Package Manager, will take your creds and it will forward it along to these different packages that LSAS already has loaded up. These packages span any form of authentication method that Windows supports. You're probably familiar with a few of these like Kerberos or MSV1 for local logons, but you also have newer things like the cloud authentication package to deal with things like Intra ID or Microsoft accounts. All of these packages will have the opportunity to take your creds and store them in its own internal data structures. These packages don't have to maintain their own data structures, though. LSAS itself has its own global set of data structures that these packages can utilize if they want. After these creds are given to the packages, any one of these packages can say, hey, I understand the format of that cred. I am going to use these to attempt to authenticate to the user. They're going to reach out to their appropriate identity provider. Assuming one of these succeeds in authenticating the user, that IDP is going to return additional user information, which can also be stored in all of these different data structures. To round out this process, assuming a user is authenticated, the LSAS process can make a little syscall to the Windows kernel, providing that user information, things like the user groups, the name. The kernel will return a handle to a token object that can be passed back to the app. And that's all we really need to cover for user logons. The main thing you need to take away is, as long as there's a user logon session, There's going to be these data structures in memory that are going to store user information as well as credentials, and that's what we're going to want to go after. One thing is worth covering, it's a little bit of terminology. Those packages that we saw loaded up, Cloud AP, MSV1, Kerberos, they have some different terms that can get a little confusing. All of those packages are considered security support providers. It's just something that does something with security, right? No, it has to be one of two flavors. Actually, it could be, there's two different forms of a security support provider DLL. The first form is, it can come in the form of an authentication package. If the DLL implements some form of logic for logging on the user, that could be a DLL that understands how to read the local SAM and then compare some hashes. That's okay. That's some authentication logic. If the DLL does that, it's considered an authentication package, which is a subterm under that SSP term. These same DLLs could also be considered a security package. A security package implements an on-the-wire protocol like NTLM or Kerberos or even OAuth 2. So a lot of times you're going to hear people throwing around all three of these terms. A lot of times they're interchangeable. For the purposes of this talk, we only care about the authentication package functionality. So you may hear me use the term provider or package, but really all I'm talking about are authentication package code in this presentation. There's been a lot that Microsoft has produced in the form of SSPs over the years. This is a thing you can go look at the LSA Whisper wiki to reference if you want. But as you can see from this slide, there's a column labeled SP for security package. A lot of these DLLs implement their own on-the-wire protocol. You'll also see a column labeled AP for authentication package. And you'll see that a lot of these DLLs act as both. That's the main takeaway. But for this presentation, again, we're only caring about the DLLs that implement AP functionality, authentication package functionality. Let's get into recovering creds. This is the component from that flow chart that we saw on a previous slide. These black boxes are storing the creds, and that's what we're going to look at. The first one is going to be the simplest, that global data structure that LSA provides for the authentication packages. That global data structure is called the LSA logon session list. It is implemented as a global variable that you can get from public symbols called the logon session table. That global variable points to a doubly linked list. There's a member of that list that points to a singly linked list called the package credentials. And there's one member we care about, which points to another singly linked list called the credentials list. In that credentials list, you're going to have a single member that is DPAPI encrypted. I'm not going to cover DPAPI encryption because it's covered pretty well in other talks. It's a basic hurdle to get over. This construct can be used by all packages if they want, but you will find only one package on Windows actually uses this data structure. The MSV1 package is the only one that does it. So it's pretty easy to talk about what data you're going to find here. Assuming you DPAPI decrypt that credentials member, you're going to find something called the MSV1 primary credential. There's been a few forms of this over the years. If you look at pre-Windows XP, it was very basic. You had a username, a domain name, and two password hashes, the NT hash and the LM hash. When XP came out, there was a small update. The SHA hash was added. This either happened in NT 5.1 or 5.2. I honestly didn't check to see which one it happened in, but it happened in XP. This lasted for a long time until Windows 10 1607. A major change happened in this version of Windows. Credential Guard came out. You're going to see in a lot of these data structures, although they typically remain stable, one of the main places they change is in Windows 10 1607 to accommodate Credential Guard. If you DPAPI decrypt that data After this version of Windows, what you're going to get is, again, the username, domain name, but you're going to have this new member called a secrets wrapper. The secrets wrapper is a, oh, cool. Just want to make sure I can draw on the screen. The secrets wrapper is going to point to a structure that's going to have a little member that allows MSV1 to interact with the Credential Guard API. That member is the cred ISO object. We're going to talk about that API a little bit later, but it's just a convenience thing for the people who write in this package. You're also going to see something in here called the credential key. The credential key is something that if you look at Mimikatz output, it's labeled just, you're going to see in the output DPAPI and then a blob of data. That is the credential key, which can be used to decrypt a user's DPAPI data. If you want more details about that, you can refer to my LSA Whisperer talk at SoCon in 2024. But if we want to get to that same data from older versions of Windows, we have to look at the secrets member. If Credential Guard is not enabled, you're going to have well, first, you're going to have this union. The union is either going to be some clear text data or a opaque blob called encrypted. Assuming Credential Guard is not enabled, we can actually look at that clear data. It's going to be your hashes that we know and love. If Credential Guard is enabled, though, this can be an opaque blob that we can't look at. But you're still going to be able to get out the credential key, which you can at least use to decrypt user DPAPI data. We've covered everything you're going to get from that global data structure. It's pretty quick, easy. Now we're going to talk about all of these custom data structures that are stored by each individual package. Now, one thing I did overlook mentioning, you're going to see this little kiwi emoji as we go through these slides. Whenever you see a kiwi emoji, that is going to be something that you can get with Mimikatz. If you see a slide that doesn't have a kiwi emoji, that's something where you can still recover credentials, but it's not supported by Mimikatz. What you're going to start noticing is about half the content we talk about isn't supported by Mimikatz. So there's a lot of credential recovery potential that's out there that just has not been implemented, which is okay. You can implement it. Okay. There's this one last data structure for MSV1. It's maintained by the package itself. It's called the credential list. It's a global variable. You can get it from public symbols. It points to a doubly linked list. It has a plain text password, as well as the username, domain name. One thing that's pretty neat about this is it has a magic value that it stores called the credential tag. There's an acronym. It's either cred active or cred deleted. It doesn't really matter, just if you want to know what that means. The important part, though, is if you don't have public symbols, you don't need it. You can scrape memory for that magic value to find these structures. The only other structure that uses that magic value is the Kerberos package. So if you find this magic value, you'll know that you're looking at either a MSV1 credential or a Kerberos credential. Another thing that's worth pointing out is you may wonder, how does Mimikatz get this data? I just mentioned there's a global variable you can get from public symbols to enumerate this data. Is that what Mimikatz does? No. If you look through the Mimikatz source code, you'll notice that most of Mimikatz uses byte signatures that it has to update across different versions of Windows to identify this data. That's not actually needed. It's more straightforward than looking for byte signatures. You literally just get the public symbols, look for that global symbol, that global variable, and then directly enumerate the data. So if you ever look at the Mimikatz source code, whenever you see a byte signature, you almost never need it. You just need public symbols. And in this case, you can use magic values instead if you want. That's all of MSV1, all the credentials you can recover of interest, I guess, from that package. Another package that's probably of interest to people, Kerberos. The XP design, if you still care about that, it starts off with a global variable you can get from public symbols called the curb logon session list. It points to a doubly linked list, right? There's going to be a lot of data that you're going to want to recover from these data structures. We're going to start top down. So we're going to start at the first member of interest. We're going to enumerate that, and then we're going to go down from there. So the cred man credentials data structure will point to a doubly linked list, which has some things that you may care about. The main one is the supplied credentials. That member will point to a primary credential structure that's going to be reused a lot by Kerberos. You're going to see that structure in other places. But that primary cred structure, which is in the LSA Whisperer development kit, it has your plain text passwords, your ticket caches, pins, that sort of thing. If we go back to that logon session entry, you're also going to see a member called primary credentials. That points to the same primary cred structure. So that's just more plain text passwords, more ticket caches, more pins that you can enumerate. You're also going to have this extra creds member. That points to a very basic structure that has only one thing you care about, the head of a doubly linked list. If you enumerate that doubly linked list, it's going to have two members called passwords. That is not what you would normally think of as a password, like a plain text password. What that is referring to is actually an encryption key. If you go to that password structure, it's going to have these members called credentials, which is going to be a blob of bytes. Those bytes are encryption keys that are used to encrypt the pre-auth data when you request a TGT. That's going to be something that you may have seen before in Mimikatz output. Mimikatz calls it e-keys, but those are your encryption keys for doing a TGT request. This did change in Vista, and then it stayed pretty stable after that. I'm going to change the slide. Look at the screen, and as the slide changes, you'll see what changed. Not much. The basic idea stayed the same. You had credman creds, primary creds, extra creds. One of the main changes here is at the top left. Instead of this logon session being a doubly linked list, that list member went away. What is it now? Well, you still have a global variable that you can get from public symbols that you can use to enumerate this, but that global variable points to an AVL tree. So at this point, you need code to enumerate an AVL tree, but you're going to see a lot of other packages are using AVL trees now. So if you implement the code to enumerate an AVL tree for Kerberos, you're going to be able to reuse that code for other packages that we're going to talk about later. Another major change that happened is where are those encryption keys stored for encrypting the pre-auth data for a TGT request? Previously, down here, you would have a thing called passwords and old passwords, and then that'll point to another data structure over here that you could look. Now, there's a new member which points to the same primary cred data structure. The reason it's able to do that is this primary cred data structure after Vista was extended to store way more credentials. Things like additional ticket caches, as well as encryption keys. Some of those members of that primary credential structure after Vista are now typed as this type called a stored credential. Whenever you see that type in Kerberos, that's going to be an encryption key. One thing I just find funny is it stores not only the current encryption key, but you also have the old one and then the older. So there's a lot of potential there. But I believe there's 3 more data structures for Kerberos that are worth enumerating. This one, notice, even though you can enumerate it, Mimikatz does not. So write your own tools and you'll be able to recover way more data. This is going to start out like every other one. Global variable, public symbols that you can get from public symbols. It will point to a doubly linked list. This one also has a magic value. Notice this is the same magic value that we talked about earlier with MSV1. So if you scrape memory and you find one of these magic values, it's either going to be a MSV1 credential or a Kerb credential. Of this, the supplied creds member is going to be one of those primary credentials, which is going to store things like the ticket caches, the pins. After Vista, it can store things like encryption keys, that sort of thing. Some of these packages store context list. Kerberos is one of them. It's just a global variable. You get it from public symbols. Doubly linked list, there's a lot more data here. Ticket caches, session keys for that. It has its own unique magic value they can search for here. The magic value stands for either context active or context deleted, but if you scrape memory and you find that magic value, it's going to be this data structure, or at least it should be. The last thing that Kerberos maintains is a session key list, global variable, get it from public symbols, doubly linked list. The thing that you care about here is there's going to be an ASN1 encrypted session key, and those session keys are the things that you pair with a ticket to be able to use the ticket when you interact with a remote host. I know I'm going quick, but this presentation is on my GitHub, so you will be able to just directly reference these slides for all these data structures and how they're laid out. The next one I want to cover is PKU2U. You may not have heard of this, but this is going to be used more and more as Microsoft pushes more people to use Intra-ID. PKU2U stands for public key user to user. It allows two hosts that are joined to Intra-ID to pass a few Kerberos tickets between each other to authenticate each other using Intra-ID as the identity provider. If you're interested in this, the RFC for PKU2U is very short. It's actually a pretty easy read. But the main thing to know is you're going to see Kerberos tickets in these data structures. They're not the normal Kerberos tickets that you imagine when you talk to a KDC. They're kind of special for the PKU2U protocol, but they still let you authenticate to things. Starts off with a global variable. You can get it from public symbols. That's going to point to an AVL tree. Each entry in the AVL tree is going to have a unique magic value. You're going to notice for the PKU2U package, they really like to use unique magic values. So even though we're showing you how to directly enumerate all this data, you can scrape for these magic values directly from memory because they are unique. The one member that we care about is the associated credentials member. That will point to one thing that we really don't care about other than the fact that it points to a primary cred. The primary cred is what you're going after. The primary cred stores a ticket cache. It also stores peer-to-peer keys to allow you to authenticate to other hosts. One thing that you may care about, though, in the intermediary structure is, again, it has this unique magic value they can directly scrape for. I honestly don't believe there's any reason for these magic values. I believe Microsoft can absolutely remove them, but for whatever reason, they give them to you. So they're very convenient. Now, PKU2U also will store contexts, just like Kerberos does. I honestly didn't look at where to start your enumeration for contexts. I'm sure there's a global variable somewhere. But what you can do is it has its own unique signature that you can scrape memory for to get these contexts. The reason I'm showing this on this screen is the context data structure will reuse some of the types that we already mentioned. It'll reuse the associated credentials, which will allow you to enumerate down to ticket caches as well as peer-to-peer keys. It also has a few members that point to this secondary cred. The secondary cred has its own magic value you can scrape out if you want, and it will store its own primary credentials. Now, on this screen, we glossed over the ticket cache. It is a little different than the Kerberos ticket cache, so it's worth doing a brief overview of that. This ticket cache is very basic. The first thing that you're going to point to is a ticket cache type, which is going to be a head, is going to store a head to a doubly linked list. Each member in that linked list is going to have a session key, which will allow you to use its ticket, which it will give you as well. These tickets, just because of how this protocol works, they're going to be TGSs, but that's still okay to authenticate to remote hosts. So, for the credential table in this package, like every other package, you have a global variable, get it from public symbols. It will point to a cred table entry, which, if I remember correctly, is one of the only cases I saw of an actual array. Don't quote me on that, but I believe this is actually just an array. Each entry in the array is going to have a member that will point to this thing called the secondary credential, which we kind of already covered, but you can enumerate it this way by either going from the public symbol. Sorry. You can either enumerate these secondary credentials by going from the public, the global variable that you can get from public symbols, or you can directly scrape for this magic value. But either way, what you want to get down to is this primary credential, which is going to store things like the ticket cache for PKE2U as well as peer-to-peer keys. Cool. Now, I know everyone here has probably heard of Derby Digest. It's the thing that popularized get in plain text creds from LSAS. This is the one data structure that Mimikatz actually enumerates, but you're going to see that there's like 2 other data structures that you can go after. So start off with global variable, get it from public symbols, points to a doubly linked list, and it has your username, domain name, plain text password. One thing to note, I've already mentioned that Mimikatz enumerates this by looking for byte signatures. You don't have to do that. Just use public symbols to get this data. Way more reliable. That's the only data structure from W-Digest that Mimikatz has ever enumerated, but there's others that you can enumerate. And these other data structures may store plain text creds where the first data structure may not. So if you want to support getting creds from W-Digest, it's recommended to support all of these data structures. The context list data structure for W-Digest, global symbol, get it from public, global variable, get it from public symbols, doubly linked list, same thing, you get plain text creds. Same thing here for the credential list, global variable, get it from public symbols. You're starting to get the hang of this, right? Points to a doubly linked list, get the plain text password from that. 2 more packages I want to cover. The terminal service package allows you to do authentication, right, for remote desktop. You're going to have global variable, get it from public symbols. There's one in each, that global variable is going to be an AVL tree. Each entry in that AVL tree is going to allow you to enumerate down to a credential structure. The credential structure is going to store 2 members that you care about. Each member is going to be typed as a primary cred. That's going to have a plain text password in it. There's also a context table data structure for TSPKG. This one's kind of interesting. The reason this is interesting is this is the only example that I'm aware of where you actually have to use byte signatures. Mimikatz is good at using byte signatures, but one thing I found funny is even though Mimikatz has code for enumerating for byte signatures or whatever, it doesn't actually support this data structure. So the one data structure that code could have come in handy for, it does not actually enumerate. But either way, the reason you need a byte signature for this is an old version of Windows, you could enumerate from a global variable called TS global context table, which was an AVL tree. In newer versions of Windows, Microsoft actually removed that global variable from its public symbols, so we can't actually get it anymore. The only reason we know its name, which is TS user mode context table, is because it was leaked in those private PDBs that were put on web archives. So we know the name of it. You can actually find it in Ghidra, but it's not something that you can directly get the offset of from, again, public symbols. Either way, you would need byte signatures to find this. If you do, it's an AVL tree. Each entry in the AVL tree is going to have a context member. That's going to store a lot of data you care about. The first member that you care about, the credential member, is going to store these primary creds, which we talked about previously. The primary creds will store plain text creds. You can get keys or other things of interest. One thing I do want to point out here that I find particularly interesting is it has a state value. In other packages we looked at, they also had state values that the way you would flip between an active and a deleted state was by changing the state value to a particular magic value. Here, Microsoft actually took a good approach. They used an enumeration, either a 0 or a 1, to represent if it's active or deleted. So here, we actually don't have a magic value to scrape memory for. So Microsoft did a very good thing. Microsoft, if you want to go update your other packages, I would recommend removing your magic values and changing them to enumerations like you did here. And this is another reason why you do need byte signatures to enumerate this one data structure. But it's the only one I found like this. Cool. The last package we're going to talk about is the cloud authentication package. This allows you to authenticate to things like Entra ID, or also log on with your Microsoft or your work accounts. Global variable you can get from public symbols, points to a doubly linked list of logon sessions. Not much in here we care about other than the user cache entry. The user cache entry will point to an entry in a doubly linked list that represents that particular user. It's going to have things like creds that are particular to that user's logon type. So it's going to have creds particular to if you logged on for Entra ID, which could be like a PRT, or for a Microsoft account, this could be like a pop cookie. The specifics, you can actually also enumerate that doubly linked list directly with another global variable if you want. The specifics of how to get creds from this are still a little bit unknown because we don't have private symbol leaks for like Windows 11. And this is really modern code that we're looking at here. This is also the one package where the data structures were the most unstable. So with the previous data structures we looked at, we saw a major change in Vista sometimes, Windows 10 1607 because of CredGuard, but really they stayed stable after that. This package, its data structures, they change a lot. So if you want a good research topic for recovering creds from Windows, I highly recommend looking at this. It would benefit the community a lot. I would appreciate your work if you wanted to do that. We talked about a lot of creds and how to enumerate them and recover them. It's hard to keep up with all that. The one way I felt maybe the easiest is coming up with a scorecard. So what you see on the screen is every package we talked about. Here's all the creds you can get from those data structures that we just mentioned. And again, if you want the specifics, either look at the LSA Whisperer development kit or refer to these slides on GitHub. If you're more familiar with authentication packages, you may notice there's a few that are missing. We don't talk about Live SSP because it's a legacy package. It was removed in Windows 10. We don't talk about S-channel because we just wouldn't have enough time. If you are interested in S-channel specifically, though, there's an older talk from Black Hat and DEF CON called Cunning with CNG. Again, Cunning with CNG. It's an amazing talk. All of the type information I, after the fact, looked at the private symbols for, and they match up. The speaker did a really great job at talking through how to recover creds specifically from the S-channel package. So highly recommend that. What we're going to do is we're going to take this scorecard. We're going to walk through some mitigations that Microsoft has implemented. We're going to take away some of these creds because we're going to say, if you enable a mitigation, what creds go away? And then we're going to walk through different logical bypasses that you can do to get these creds back, or at least most of them. But to wrap up this section, most of these structures are stable. The few exceptions are in Vista, Windows 10 1607 because of CredGuard, and that Cloud AP package because it's highly unstable. Even though you may see in Mimikatz that it uses byte signatures all over the place, you don't need to do that. Just use public symbols. And if you don't have public symbols, most of these packages have magic values that you can use to identify this data in memory. Also, half the slides we just covered are not covered by Mimikatz. So let's say a package offered a logon session list as well as a context list. You may find creds in the context list that don't actually exist in the logon session list. And it may be the case that Mimikatz only enumerates the wrong data structure in that scenario. So it's highly recommended to write your own tool, look at all of the data structures, and you're going to find more creds. So let's move on to CredGuard and a few other mitigations. CredGuard is something that was added in Windows 10 1607. Officially, it's only supported on two versions of Windows, Education and Enterprise. Technically, you can get it working on Pro as well, but there's a caveat. You have to install Enterprise, then enable CredGuard, then change the license on that host down to Pro. So for the purposes of this talk, we're just going to say it runs on Education and Enterprise. It also only supports 2 packages. So all the creds we talk about, only the MSV1 and Kerberos package creds are actually protected. The best way to think about this is Credential Guard is essentially taking your creds as you give them to LSAS and stores them in a VM. That's not actually the case. There's more details, and if you're interested in that, there's a talk at the bottom that I recommend looking at. But conceptually, it's easiest to think about this as CredGuard takes your passwords and puts them in a VM. The other thing it does is it will limit what operations you can do on those creds. So if there's a operation to take the cred and perform a dumb hash, like an LM hash on it, it will prevent that. If you want to do research into CredGuard, there's one thing that I find highly valuable, which is looking at the CredGuard APIs. You can get these APIs from those private symbol leaks, but there's 2 for the 2 different packages CredGuard supports. I'm going to show you a basic excerpt of all the things you can do with these APIs, or at least all the things LSAS can do. All I want you to see from here is if you look at a few of these, you can start getting an idea of what it's protecting. We mentioned that there's a credential key, which allows people to decrypt DPAPI data. We see that name, credential key, show up in these APIs. So you can infer that CredGuard is protecting MSV1 credential keys. So you don't actually have to, as long as you have these API lists, you don't really have to do a lot of reverse engineering. You can take some basic inferences to figure out what's being protected. Another thing you can do is you can look at Microsoft documentation. Microsoft documentation overviews a lot of the high-level operations that CredGuard code will attempt to prevent. Things like requesting a master key encryption key to decrypt a user's master key to do DPAPI-related tradecraft. It will prevent that. It will prevent you recovering things like the SHA, hash, or generating NTLM v1 responses. Similar things for Kerberos. If there's a older antiquated protocol, it'll block it. It'll also block things like unconstrained delegation because that allows you to still recover a TGT, which it tries to prevent. Specifically with the TGT, it doesn't really care if you get the ticket. It cares if you get the session key because that's what you need to use the ticket. So let's take our same scorecard. Let's take our knowledge from if you looked at the API names and you looked at the Microsoft documentation, and let's apply it to see what creds are blocked. Notice, again, it's only 2 packages. There are other mitigations, though, of course, that Microsoft has added over the years. These are the main ones. It has disabled wdigest, so it won't be used at all. So we can just take that off the scorecard. It allows you to run in LSAS as a PPL, which is supposed to prevent you from getting access to LSAS memory altogether. Remote guard is supposed to prevent plaintext creds going to a remote host when you do RDP authentication. Personally, though, I've never really seen clients use it because it becomes a pain for the user to retype their password all the time on that remote host. So we're just not going to talk about it. You also have things like the TPM, which is used to store some Cloud AP creds. I do have a little emoji, a liar emoji, next to NTLM1 removal. Microsoft has publicly stated that they have removed the NTLM v1 code from Windows 11 24H2 as well as Server 2025. That's not true. You can still request NTLM v1 response generation if you're doing that locally, which we're going to talk about later. The only thing that will block this is CredGuard. So if CredGuard is not enabled, you can still request someone's Intune v1 response and then crack it with a rainbow table back to a usable NT hash to use on the network. The last thing is just there are these little plugins for LSAS called NPR plugins. They can receive a plain text password when a user logs on, and they just stop that from happening anymore. So let's add a few of these mitigations to our scorecard. If we disable wdigest, of course, that package goes away. And if you add LSAS protection, which is LSAS running as a PPL, almost everything else goes away. The only thing you still have left is the ability to get tickets from Kerberos. And if it's TGS, you can get the session key. But again, CredGuard will block you getting a session key for a GGT, which will prevent you from using a TGT. Now, the last section. How can we get around these mitigations to still recover some of those creds? There's one concept that is super powerful that I want to cover. Doing an authentication package call. All of these packages that we talked about, they have their own custom functionality, their own custom APIs that you can actually interact with. And it's a simple call. It's a Win32 call called LSA call auth package. It's very basic. With that Win32 call, you can submit a blob of data to LSAS to forward along to a package to interpret. If that package recognizes your blob of data as an API call that it understands, it can send you back some output data. Now, a few years ago, I gave a presentation at SoCon called LSA Whisperer. You can go to refer to that if you want, but basically in that presentation, I reverse engineered every single API for every single package that Microsoft has ever produced. And from that, I looked at each API and said, is this useful to a red team operator? There's a lot that you can use for like host enumeration and some other tradecraft, but it became very valuable for cred recovery. Three packages in particular have a set of APIs that become incredibly valuable. Of the Cloud AP, Kerberos, and MSV1 packages, these are the APIs that they internally implement that you can interact with. If you're a red team operator, you've probably already seen the functionality for Kerberos, which allows you to request a ticket. But for Cloud AP, you can do things like get a single sign-on cookie for a logged on user. Or if they're using a Microsoft account or a work account, you can get their POP token to still authenticate on the web as them. If someone's logged on with a local account, or even if they're encrypting data locally with DPPI, you can use a few APIs from MSV1 to get their credential key. And their credential key is going to either be an NT hash, a SHA hash, or something called a secure credential key. All that matters is you can use it to decrypt DPPI data. The last thing from MSV1 is LM20 get challenge response. What that does is it gives you an NTLM v1 response. So we can map that to things that you would see on the scorecard. If we put that and apply it to the overall scorecard, you're going to see a lot more data get added back in. I glossed over it, but there is an asterisk next to the NTLM v1 response. The reason there's an asterisk is you'll only be able to request those NTLM v1 responses if CredGuard is not enabled, which is in a lot of environments because you have to have enterprise. But if CredGuard is enabled, you're not going to be able to get that. If you can make that request, though, I highly recommend going after it because that API allows you to specify something called a server challenge, which is the only thing that's used as a salt. When you request an NTLM v1 response, the server challenge is used for assault to prevent you from doing things like easily cracking that hash. But this API allows you to provide that, so you can provide a salt that you know aligns with a rainbow table to instantly get NT hash recovery that you can use on the network. So it's a very useful technique. Cool. Now we have lots of other abuses that have come up over the years. You don't have to go after user memory. Of course, those creds stored in many other locations. You can go after the databases that are used by those IDPs. That could be the local SAM from a registry hive or ntds.dit if you're looking at a KDC. There's other Windows technologies that store creds, of course. You also can take a roundabout approach to access these databases. You can look at file system forensics, so you can do things like looking at attached drives and parsing the MFT yourself. Or you can look at things like the VHDs or VMDKs for virtual machines. If you do forensics on a VHD or a VMDK, you can recover things like the SAM or the ndds.dit and then get your password hashes. There's been methods to bypass LSAS protections, so LSAS run as a PPL, that have come out over the years. You can do things like you can load your own authentication package or your own LSA plugin, and people have just found other exploits to get around PPL. So if you do that, you get code execution in LSAS. You'll be able to read memory and enumerate those same data structures we talked about. There's also specific logical bypasses that you can apply to Credential Guard. So one thing that came up this year was a talk at SoCon, I'll pull it up in a minute, by Kerry Coburn. Kerry Coburn very basically described how he reverse engineered a part of Credential Guard that prevents you from requesting a TGT with a valid session key. He looked at what check was being performed, and he noticed Credential Guard will check the spin of the ticket that you request and see if it matches the literal string KRB TGT. He then looked at the RFCs for Kerberos and said, are there ways I can obfuscate the spin? And he saw, yes, there are several ways in the public RFCs for Kerberos where you can encode the spin. Very basically, he applied a valid encoding for the string KRB TGT, passed that in a request to get a TGT from LSAS. Credential Guard didn't recognize that string and said, oh, this is something else. And it gave back a valid TGT with a valid session key. One thing I'll note, Kerry in that talk only covered one encoding scheme. Those RFCs, and that's the only encoding scheme that Microsoft patched. Those RFCs cover several encoding schemes. So if you want another research topic to go after, I highly recommend looking at the other encoding schemes for spins and the Kerberos RFCs. It is very likely that you're going to find another bypass for CredGuard in the case of getting a valid session key for a TGT. Highly recommend. Okay. Now, there's other things you can do. You can indirectly access memory, such as PCI Express, if you want to get physical memory and go from there. Or if you're dealing with a virtual machine, you can go after things like the VMRS for Hyper-V or the virtual machine snapshot files for VMware or ESXi. You can go from that and treat it as normal physical memory and get down to what virtual memory would look like for LSAS and then enumerate the same data structures. Lastly, the oldest way, of course, is keylogging, but it's very basic, so it's not worth covering. Let's apply some of these logical bypasses to our current scorecard. If we add in a PPL bypass, of course, we're going to get a lot of creds that are not protected by Credential Guard. You're still going to see some things still blocked out, like WDigest, because it's completely disabled, but things that are still enabled, like Cloud AP or PKU2U, you can get that data. I had a friend ask me a few months ago, he said, is it still worth injecting into a PPL process? Or just being able to read PPL processes memory? Absolutely. If you have that for LSAS, these two packages you can get very useful data from. Let's say you have a credential guard bypass like what Carrie covered, and there are very likely to be others. Please go read those RFCs. You can very likely get the session key for a TGT to be able to actually use it on the network. Cool. So this is our final scorecard after we covered the mitigations that Microsoft has implemented, as well as a bunch of logical bypasses. If you take a moment and you look at this and you think, what if I was a red team operator? Would this be useful? You're probably going to walk away with the conclusion that anything you would ever care about doing, you can do with this set of credentials. If you want to decrypt local data, you can do it by getting the secure credential key from MSV1 and decrypt that DPPI data. If you want to authenticate on the network with a local account, you can request an interim v1 response, use a rainbow table to crack it to an NT hash, and you do pass the hash. If you want to do Kerberos, you got your tickets right there with their valid session keys. If you want to do anything cloud-based, you have basically everything you want here. Cool. So one big goal I had for this presentation is just to give you these treasure maps. So if you wanted to rewrite Mimikatz, you at least have a good starting point. You have these resources of the private PDBs that you can get from Web Archive. So you just go search for that if you want. You also have the LSA Whisper development kit, and you also have these slides where I know there's a lot of flowcharts on the slides, but you have them as a nice reference where if you write your own credential recovery code, you know where to start. Some other things I want you to take away from this is it's not really that difficult to get creds from LSAS memory. One of the main reasons it's not too difficult, even though you can look at the Mimikatz source code and go, Mimikatz, it's using all these byte signatures. I don't want to maintain that. You don't have to. You can use public symbols to identify these global variables that are the starting point for all of these data structures and then go from there. If you don't have public symbols, you don't even need them in a lot of cases. You can scrape for a lot of those magic values that we mentioned and then go from there. Another thing I want you to take away is Credential Guard and all these other mitigations, they're not that scary and they're really not that bad. They're gonna prevent you from getting everything. Like unless you have an actual keylogger, you're probably not gonna get plain text creds, but you also probably don't need it. All the other creds that you can still get if there's a valid logon session is probably everything that you would need to decrypt that local data that you care about or to authenticate on the network. Now, for the few people here that are acting as a defender, still recommend update to the most recent version of Windows, still enable these mitigations. It still provides roadblocks, even though they're not the end-all be-all. And if you work for Microsoft, I do have one recommendation. I mentioned earlier, please remove those magic values. They're not useful for anything other than cred recovery. But if you were to do one thing, I would recommend adding support for PKU2U into Credential Guard. PKU2U is going to be used more and more as Microsoft pushes people to use Intra-ID. So it's going to be more valuable to attackers in the coming years. So that's something that you can easily add into your Credential Guard technology. We are over, but I am the last talk of the day. Does anyone have questions? Well, you can still grab me afterwards. I'll just be in the hallway. And then again, there's a lot of flowcharts in these slides, but they are on GitHub under my account. So you'll have them there as a reference. Thank you.